Right. So I proved this lemma, and especially for you.
Okay.
So the lemma is that when you have a Gaussian integral perturbed by this formal power series n over 2 minus 1, sum over n factorial, sum over I1 in, v I1 n x I1 x in, dx. So then it is equal as a formal power series to this expression. The first term is the result of the Gaussian integration, and then the rest is the power series in h, I h to the minus the order characteristic of gamma, f of gamma divided by the number of automorphisms of f. So where f is the weight of the graph, I explained how to compute it. And this expansion is also called Feynman diagram expansion.
So let's say what you really proved was this in a case when you had a polynomial.
But
I mean, you proved this lemma.
Yes.
This was really a theorem about when the expansion was a polynomial.
it's a formal power series in H.
Yeah.
So it's really, on the left you have formal power series in H, and on the right you have formal power series in H. And the statement is that these two formal power series are the same. And this integral is understood as the integral epsilon goes to 0, and here it is.
Yeah, I mean, in order to not confuse, okay.
So it's a formal power series, we integrate it, and that's the result of the integration of formal power, of the formal power series.
And
So now let's
probably
consider.
there would be some kind of analytic statements, right?
Yes. So now let's consider the more interesting analytical statement. So let's return to the oscillating integral that I mentioned already. So let's make the following assumption that M is compact with the volume form dx. F has finitely many critical points, simple critical points. So then we may ask the question, what is the asymptotical behavior of this integral as h goes to 0? And then it's the standard piece of stationary phase approximation that says that under this condition, this integral is asymptotically equivalent to the contribution sum over critical points, and then the integral over the small neighborhood around the critical point. And then what does it mean, this small neighborhood of a critical point? That's when we approximate the manifold by its tangent space. So essentially, what it means is that it's asymptotically equivalent to the integral over Rn, where Rn is the tangent space. So we identify it with the tangent space at point A to M, and then e to the f c a t over h dt, where f of a t is the Taylor expansion of f. So it will be f of a, it's a critical point, so plus 1/2 t t is the local coordinates, f second derivative at plus sum over n greater equal 3, 1 over n factorial, sum over I1, In, partial derivatives with respect to local coordinates t, and then so you see this integral is actually almost like this one, because we can so what we want to do now is we want to compute the sorry, it's still over small neighborhood of A, but then let's say epsilon neighborhood, which we can identify with some small ball in the tangent space.
Yeah. When you say asymptotically equivalent, what does it mean exactly?
So it means the following. Say if you have an expression like this, C over H, and then polynomial of degree n in H, asymptotical equivalence means that this difference divided over H to the n plus 1 goes to 0 as H goes to 0. Like asymptotical power series.
So this has to hold for all n. So
And that's for all.
Yeah.
Yeah, yes. If you have a power series.
yeah, so up there one could say IH minus the stuff on the right is equal to O of H to the minus n plus 1 for all n. You know, it decays faster than any exponent.
This power series may diverge, but for every n it has this property.
And sort of, if one wants to make, so right where you've written asymptotic equivalence, the thing on the right is not yet of this form, but one could just say the difference of the two is equal to big O of H to the minus n for all positive n.
Wait. First. Okay, so first, so you have two numbers.
Two sequence of numbers.
Two sequence of numbers, depending on
H.
H.
And now we want to define what it means for those two to be asymptotically equivalent.
Yeah.
So basically,
Depending on the powers of it.
And let's do it precisely. So but we could call them IH and IH prime. Prime on the i's.
Yeah.
And it just means take the difference, take the absolute value,
Yeah.
and one way of formulating, divide by h to the n plus 1. And that goes to 0, or h goes to 0 for all n. That's the condition of two quantities to be asymptotically equivalent.
yes. So this function of H is asymptotically equivalent to this formal power series in H. Basically, it's a collection of numbers
Yeah.
A1, A n.
Yeah. So now,
If this happens, where Pn is this polynomial.
yeah, this is all good, but the thing is, the thing on the right is not of this form yet. So
Well,
therefore,
it's going to be in this form.
it is going to be in the form, but we can actually make sense of it just by having two quantities, IH and I prime H. And we just substitute for I prime, we just put it instead of e to the IC over H, Hn of H, we just write I prime of H. And then there you see the condition right there, for all n. You have to say for all n.
But wait, now I'm confused. I mean, so
And maybe you could write that, Corey. We
Yeah.
divide two quantities, I of H and I prime of H. What does it mean, those two asymptotically equivalent?
yeah, or that something goes asymptotically to 0. I guess that's.
I don't want to go into that.
Because it's really simple and just
No, can't you write down?
Okay, sorry. It just means, so let's write IH is asymptotically equivalent to IH prime, if and only if for all n, the difference between IH and IH prime times 1 over h to the n goes to 0 as h goes to 0.
Well, to me, it's not exactly what Colin means, because IM is a function, is a real function which depends on h.
Yes.
And h prime is a form of our series which usually diverges.
Yes, it doesn't matter whether diverge, it's the difference.
Yeah, but you need to
Makes sense.
IM prime, but IH prime nth. So you take the first part of your
Yes.
divergent series. Now it's convergent.
Yes.
Now, so you need to take, because just
Right,
trigonometry. So you
but
need to take the
what
difference and this goes
here
to
you
0.
need to do something.
Give us, I mean,
Exactly.
I actually disagree with this.
You don't agree with this?
Because this expression to me has no sense because I and h prime is not a function.
What is this?
I don't want to make
This is a function.
Right, and so we want to make sense of what it means these two are asymptotically equivalent. There are actually two notions. There
Right,
is
right, exactly.
there are two notions,
Exactly.
and these two notions are now written on the board.
Yeah.
Here I have two things that are well defined as functions of h, and now I specify what it means to be asymptotically equivalent.
Great.
Here I have something different, because here I have one quantity which is a well-defined function of h, and I have something that's only an asymptotic expression. And then we truncate for each n, just like you said over here, Colin. We truncate the right-hand side,
I
and
actually,
then we have the two different notions. on the board.
actually agree, yes, that's,
Okay.
yeah. That's,
Yeah, so you should really like the
So-
I prime. They should have two indexes. It should have n and h.
No,
no, that's the
two
point.
different notions.
For every n, this difference goes to 0. So what it means is that they have the same asymptotical form of power series. These two expressions.
But I am prime. This is only a power series in what you have written.
No. We see there are two notions. First, the asymptotical equivalence with the formal power series.
Yes.
That's the first notion.
Yes.
Second notion is the asymptotical equivalence of two functions.
Right.
So if you have two functions with the same asymptotical formal power series, then if you will subtract one from the other, it will vanish so faster
like
than h to the n.
Yeah.
That's the state.
And in the above equation, we need both. So in the first equation, or the first squiggly equation, we need the notion I wrote. And then once we get on to what we want to finish with, we need Colliers' notion.
Roughly speaking, when you have an oscillating integral e to the I n x dx, well, you have contributions from the critical points on the real line, but then you can also do analytical continuations, and then you will have exponentially decaying contributions from the steepest descent method. And so all of these critical points will contribute to the asymptotic. Somehow here we count only those which come from the critical points on the real line. And if you will subtract this contribution from the integral, only the ones that are exponentially decaying will contribute. And for this exponentially decaying things, this will go to 0.
Yeah. So now you have formulated it completely without formal power series. I mean,
Yes.
Yeah.
Yes.
So just
Yes.
statement about functions, and
Yes.
then you can go on and mumble something about formal power series. But you haven't done that yet.
Well, the definition is right there.
Yeah.
The definition is what Collier wrote.
Yeah.
Sure.
Yes.
With the all n promoted a little bit. Oh, I would have put the all n in the box.
Yes.
Yeah. Okay, great.
Yes. So this is what it means that
Exactly.
But the whole strategy here is to replace analytical objects, which require analysis, by algebraic objects, which are formal power series, and see how far it can go. So, okay, so now we want to replace these integrals by the asymptotical expansions over there. So how do we do this? let's look at the integral, say in some small ball in Rn of the expression 1 over h I over h 1/2 x dx minus some this expression. So, and I put t here. So here it will be h to the n over 2 minus 1 over n factorial sum over I v I1 in t I1 t I. Roughly speaking, this is what we should integrate in each of the contributions from the critical points over there. Now we want to take the limit h goes to 0, so let's first change the variables to the square root, just as we were discussing. So then it will be the ball of radius epsilon over the square root of h e to the I b x dx over 2 oh, I'm sorry, there is nothing here. Yes, this is the Taylor expansion of our function. And then we will have these powers of h. So it will be from the change of variable h to the n over 2 and then h to the n over 2 minus 1 n factorial sum over I vi x dx. So you can see that if I put h, well, it's a formal power series, so I can't quite do put h in the denominator here. But this tells us that the asymptotical expansion of such integral is so integral, and then if we take h to 0 faster than epsilon to 0, in this mu x variables, it will be an integration over the whole Rn. So in this asymptotical expansion, we take h to 0 to faster than we choose the size of this small neighborhood above critical point. So the result is that from the integral over this point h dx is given by that contribution if you take into account the power of h. So it will be equal to 2 pi h n over 2 e to the I pi over 2, the signature. And now let's identify the elements here. So B is F2, but V is minus nth derivative. So just to get the signs correct. So it will be this over the square root of the determinant of F2 and then 1 plus the sum over non-empty Feynman diagrams IH to the power minus the Euler characteristic of gamma, the automorphism group of gamma number of elements, and then the weight of the diagram gamma, and in the computation of weights we should take into account that B Ij is simply the matrix of second derivatives in these local coordinates. ij vi1 ik is simply minus kth partial derivative with respect to local coordinates x of f at point A. And so we have a, so I outlined the proof of the following statement, that this integral is asymptotically equivalent as h goes to 0 to the formal power series, which is sum over critical points of f, and then we have e to the I f of a over h plus I pi over 4 the signature of f second derivatives, the determinant of f2 of a times the sum over all non-empty graphs ih to the power minus the order characteristic of gamma, and then these factors that became familiar. So this is the
do you have to be more careful here? Or, I mean, so now you say this epsilon, this depends on h. So I mean, the right term in this asymptotic equivalence, you really redefined it now. Now it's integral over m alpha epsilon, where epsilon depends on h.
yes.
And then you say that as h grows, this epsilon
as h goes to 0.
As h goes to 0, epsilon will go to infinity.
No,
Or
stay.
but I mean, the integral will essentially become the integral over. Yeah. Right. Yeah, right. Yeah, exactly. And then you do this variable transformation, which transforms the integral to something. Yeah.
Mm-hmm.
But still, I mean, now you replace this integral with what you get in the limit. And I mean, do you have to be more careful about how
Well,
this asymptotic?
this is not, what I explained is not a proof.
Okay.
The proof has, I mean, it would require just exactly what you said, some estimates and needed to...
Yeah, okay.
No, I think that part is all right, provided there's some non-degeneracy on the quadratic term, on the second derivative of f. If the second derivative of f, if it's a non-critical, it's a non-degenerate critical. Yes, if it's a non-critical, non-degenerate critical point, then it works. But what the where one has to be more careful is in the first, namely the localization just to the critical points. There, I mean, there might be situations where, first of all, not all of the critical points needs to be taken into account.
But if f is real,
if all critical points are non-degenerate, they all has to be taken into account. They all contribute in the same way.
If f is real, yes, but I mean, in order to apply this is the Taylor method, or there's no phase approximation, right? And one needs actually to figure out that f has a certain behavior relative to the critical points in order for this to work. I mean, this will not always work. I mean, there are some properties that the f needs to satisfy in order for this to work.
But you say it always works if a is a
Is a Morse function.
If it's a Morse function.
If it's a Morse function, then it works.
If it's not a Morse function, you have to be more careful.
Yeah.
It sometimes works and sometimes it doesn't.
Yeah.
Okay.
Yeah, that
Okay.
all right. So this is the provided that so just let me make a disclaimer. So again, I really didn't prove this theorem, but I mean the proof is more involved. But that's sort of the idea of why it's true. So So we have this asymptotical expansion, and now you see the idea is if we have an infinite dimensional manifold, well, we can make sense of the integral over of such integrals over infinite dimensional manifolds in two ways. First, we can try to really define it, measure theoretically as an integral. But second, we can just well, we can study formally the asymptotical expansions, this formal power series representing something that we want to study. So like when we have a path integral, this idea of the path integral, the integral doesn't make sense. But what might happen is that all ingredients on the right side, all ingredients of this formal power series, they make sense. And if they do, then we can try to formulate this formal semi-classical quantum field theory where path integrals are replaced by these formal power series expansions. And that's essentially what happens in perturbation theory and quantum field theory. So, but it was rightfully noted that all this works when critical points are simple, when there are finite many of them. Simple means that this matrix of second derivatives is not zero. So now, what if they are not simple? What if the matrix of second derivatives is degenerate? Well, this degeneracy can happen in many different ways. But let's remember what we have in mind. We have in mind quantization of gauge theories. And in those theories, the action is invariant with respect to the gauge group. And the degeneracy of the action comes in a very special way from the action of the Lie group on the space of fields. And so let's look at the finite dimensional analog of this situation. So basically, now let's look at the following situation. Suppose that we have such integral. Again, just to make sense, so that it would all make sense, let's assume that M is compact. So we need volume form. Now I assume that there is an action of a compact Lie group on M. Dx is invariant. F is invariant. And the question is the same. How to find the asymptotical expansion of this integral as h goes to 0? Well, so here's one possibility. Everything is, let's assume in addition, just to make things simple, that the action is free. So there are no stabilizers. Which is rather unrealistic assumption, but let's assume it anyway. So what it means is that generically there are no stabilizers. There could be some set of measure 0 with respect to this dx, where points may have some stabilizer. So let's make one more assumption. F is critical simple G orbits. So let me put here generically no stabilators. So now, if F is critical at some point, there is the action of the Lie group, so it will be critical on the whole orbit of the group. So the assumption is that those orbits that pass through critical points of F, they are isomorphic to G. These are generic orbits, so these critical points have no stabilizers.
Does the word simple mean? Simple.
Well, simple means that this orbit is isomorphic to G. It means that there are no stabilizers. Okay, so this is the second assumption. And then the third assumption is that all critical, so points are simple in M mod G. So we made an assumption that that the critical points lie on simple G orbits, so it means that in the vicinity of the critical point, they we have sort of some meaningful M mod G. So on this M mod G, the function should have simple critical points.
But simple
In other
means
words,
non-degenerate.
simple means non-degenerate. Yeah, there are two meanings of simple. So, non-degenerate critical points, all it means is that the the degeneracies of these critical points, they happen only in the direction of the action of the Lie algebra. It's not more degenerate than because of the action of the Lie.
Yeah, so the Hessian restricted to the normal bundle is not degenerate.
Exactly. Yeah. So then, if this would make sense, we would write it like this. Where X is the G orbit through X, and now we're integrating over the space of orbits, or in other words, over the quotient space M mod G. And then by the assumption, all critical points of function F in this space are non-degenerate, so we can use the this expansion to write such an integral. Well, the problem is that, say, for future purposes, the quotient space, say, if you will take connections and you will model out by the gauge group, this will be some kind of horrible infinite dimensional quotient space that is very difficult to work with. So instead of working with the space of orbits, what we can do is we can choose, say here is the model for M with the G orbits. So we can either work with the abstractly with the space of orbits, or we can choose a cross section through the space of orbits. And we can model this space as a space of functions on the cross section. And then, so that it doesn't matter how we choose this cross section, it's just like a different system of coordinates. The integral will not depend it, but so the way how you integrate will look slightly different. So, so again, in order to avoid working with these complicated quotient spaces, there was a technique developed in gauge theory, which goes back to the works of Faddeev and Popov. It's called Faddeev-Popov quantization, or Faddeev-Popov ghosts. And then it involves some fermionic degrees of freedom. So before we will discuss this, we will discuss some Grassmann integrals. So there are so-called ghost fields, which are fermionic or related to Grassmann algebras, to the exterior algebras of some vector spaces. So then there is something that's also, so this is Faddeev-Popov. And then there is something that is called BRC, algebraic formalism, and this is Becky, Rive, Stora, and Tuzin. So these people, they essentially realized that somewhere inside of these computations there is a hidden Chevalier complex of the Lie group G, and here it manifests itself in this quotient, because under all these assumptions on M and G, we can identify functions on M mod G with the zero cohomologies of the Chevalier complex for the Lie algebra with the coefficients in the space of functions on M. And basically, these ghost fermions, using this interpretation, they sort of have the natural place, sort of mathematical placement. So basically, these are the coordinates in this Chevalier complex. Chevalier complex is the exterior algebra of G tensor this. The exterior algebra of G are exactly these ghost fields. So this is the outline of what we will do today. So the goal for today is to write this integral as the sum over graphs again, but this sum will be more involved. We will not apply this asymptotical expansion for this integral. We will somehow modify the original formula, and this modification will involve some Grassmann variables and integration of Grassmann algebra. So as a result, the nature of Feynman diagrams will be slightly different. And it's exactly those Feynman diagrams of this slightly different nature that are used all the time in Yang-Mills theory and in, for example, if you want to do semi-classical asymptotical Chern-Simons theory.
Sorry, what did you mean by Fm divided by G? The first
Functions.
functions.
And yeah, C infinity functions.
Yeah.
All right. So then the project for the next 2 hours is the following. First, I will recall what is the Grassmann algebra and Grassmann integration, plus the Grassmann version of this statement, and then we will see how in this finite dimensional example this Faddeev-Popov technique works, and then if time permits I will discuss the BRST explanation of the fermionic integrals there, and then after this we'll move to Feynman diagrams in Yang-Mills and Chern-Simons theory. So that's the plan, and we still have 5 minutes, so I can just start with the.
So what you've written down, that's just invariant theory, or is it more subtle than that?
But
I mean that equality as C infinity is equal to H naught.
It's more subtle, but in this particular, well, you know,
I mean the functions of m divided by g. That's the function of m which are invariant under g.
let's
Yeah.
let's replace
level.
everything with the algebraic
But-
setting, and
yeah.
then it's true.
Yeah. So I mean, but it's not quite what you mean. It's more subtle.
I don't want to be absolutely precise because I don't have to. Because for the purposes of this developing these Feynman diagrams, it's not really important. We will,
Okay.
but I mean, in order to completely make sense of this theory, we should, of course, make it precise. Yeah. So maybe I agree. Maybe it doesn't make sense to start this now. So instead of this, I'll be happy to answer any questions. Yep. Up now. So essentially, so just one more word about the future plan. There is one theory where this formula can, this idea of the semi-classical quantization of field theories, not by considering this integral, but by replacing it by this formal power series, there's one case where it can be checked. It's quantum mechanics, where the quantum field theory is completely determined by the Schrödinger equation, and you can compare the results of the definition from the Schrödinger equation with this formal power series. Remarkably, they coincide. So I think the plan now, I still want to finish this finite dimensional integrals for the case when the Lie group is involved. But then, before we'll start gauge theory, we'll have a short discussion of the quantum mechanics.
So the assumptions you make, I mean, are they just to make things simpler, or are they actually not too unrealistic? I mean,
Which assumptions?
the assumptions over here, 1, 2, 3.
There we see, under these assumptions, what I will do is correct.
Mm-hmm.
So they're sort of, in this sense, they're natural assumptions. For gauge theory, there are a group of anomalies, and there are, I mean, these are infinite dimensional spaces. So you see, if somebody will give me a definition of the path integral as an integral, then I would really start to worry about all these assumptions in Yang-Mills theory. But the problem is that there are no such definitions. So because of this, I'm not sort of worried too much about it. So the idea is to define the asymptotical expansion of this integral, and then to see if it works in the Yang-Mills theory. If it works, then we will take this as a definition, I mean, according to physicists. I'm not inventing anything new here, it's just maybe I'm slightly repackaging the very conventional things. So yes, in this case, I need these assumptions in order to derive the asymptotical expansion. In the Yang-Mills theory, I just take the result of the asymptotical expansion, and that will be the definition. And all these problems with anomalies, well, they just indicate that things are not that simple. So not that simple at two levels. First, difficult to define the integral, and second, even if you define the integral, to have this program work, so there are some natural abstractions to this.
Well, it seems to me that the conclusion that the action is free is just to make.
No,
you can easily remove it.
No, this I can easily remove. This is just proof. Yeah. This is just for simplicity. Well, the rest is more essential.